Welcome everybody, thank you for joining us. Today we will continue with our training session where we introduce different tools and methods available on our HAL computer system. Today I'm very happy to introduce Dewey Mu. Many of you already know him well enough. Dewey is our systems engineer who is responsible for actually running the system and also providing user support. I'm sure many of you already interacted with him. And so Dewey himself also deploys and manages all kinds of tools and systems and platforms and software on HAL. And also he is very knowledgeable with regards to how to operate them and how to set up the environment for users to be able to use the systems and the software tools. And today he's going to give a tutorial on H2O tool, which is sort of a code-free approach to conduct machine learning. So Dewey, please take it from here.
All right. Hi, everyone. Welcome to this training session. Today, we're going to introduce how to use H2O AI to run machine learning jobs on HAL system. So let's get started. So first is the introduction of AI, machine learning, and deep learning. So artificial intelligence is not a new concept. Actually, in the year of 1950s, there are already some discussion about how to make machine that thinks like man or doing jobs like that only man can do. So one example is in the movie industry, there is a iconic sci-fi movie 2001, A Space Odyssey, which in which there is the first AI concept computer that afraid to be shut down. So he killed almost nearly everyone on that spaceship. And that computer is called HAL 9000. Yeah, it's a code joke. And in the year of 1980s, there's another concept start to be discussed, which is machine learning. Machine learning is considered as a subset of artificial intelligence, which means the differences is the people do not explicitly program the machine learning algorithm. We just set up a set of rules that the machine will learn how to do the job by themselves. And another wave came in 2010. It's called deep learning. The deep learning is actually not a deep thinking or deep understanding. It's rather a deeper representation of data set. So let's continue. So this machine learning and deep learning is a interdisciplinary field. So it combines the domain science, mathematics, and computer science. So, I mean, it's hard to acquire all the expertise in all three regions, but also due to the technical advance, there are a lot of good tools can help researchers to enter the data science region with a relatively lower barrier. So someone may ask, but why now the machine learning and deep learning start to get more and more popular? There's three reasons. First is the hardware. The high performance GPU and TPUs emerges since the year of 2010. the NVIDIA, to be specific, is set up their goals to all in AI in the year of 2015. Also, the second is the data set. Due to the development of the internet, collecting very large data sets is become from impossible to possible, which is provide more than enough food for researchers to implement their algorithm of deep learning and machine learning. The third one is, of course, algorithm advances. We now learn that there's always have new activation functions and optimization schemes being developed to solve different type of deep learning, machine learning problems. Today, the software we want to introduce is called H2O AI. The H2O AI is the company behind the open source machine learning product like H2O, aimed to make machine learning easier for all users. H2O is an open source, Java-based, in-memory, distributed machine learning and predictive analysis platform allow you to build and productionize your machine learning model, which contains supervised and unsupervised model in both R and Python, as well as a simple to use web UI called Flow. Today, we will majorly use this H2O AI Flow. So maybe some old user has know that we have been giving this similar talk in the last 2 years, which I use majority of the time is to introduce the machine learning algorithms. So this year I want to make some change. So I want to focus on how to utilize this H2O AI Flow to help our users to for their research project. So I'm going to jump between my slide and the H2O AI Flow to show our users how to use it. So now is the time for our users to start a H2O AI session for themselves. First is to start our HAL on demand web portal. After you log in, you can see we just made some few changes. We have we had a few shortcuts for different services. Our user can click the H2O AI one, and then this form will show up as shown on the right-hand side screenshot. The user can input 2 or 3 hours for the runtime and use UI_UC_47 to fill in the name of the reservation field. And then after lunch, you will see a job being submitted, and if everything went smoothly, within a few seconds, you should see your job is up and running. There is a connected to H2O AI button shows up. Just simply click that. You will be moved to the H2O Flow interface, so that in the next few hours presentation, if you bored with my presentation, you can always try out this very interesting tool for yourself to experience the easy to use and very productive software. And so I will give you like 1 or 2 minutes to connect, and you can, if there have any problems, please just type in the chat so I can help you to fix if any problem there. basically, as we can see, this is the HAL on-demand main page. By clicking the HAL AI flow, you will be going to the this site. You just type 3 hours or 2 and UI_UC_47 and click launch. And then this one. And then within a second, you will have that. After that, you're gonna have a H2O flow ready for you on our HAL system. So can everyone get along already? Is there any problem? If you successfully start the H2O flow session, please also let me know. Can you type in 1 or something? Okay, no answers.
Hi, Professor.
Hi.
So I think I have trouble accessing to the website, the HAL on demand. I don't know why. I just cannot access to the website.
Did you set up a HAL account already and set up the dual software on your phone?
I didn't.
Oh, yeah. If that's the case, yeah, you need to set up the account and also set up a dual app for your push authentication.
Okay.
Yeah.
Got it.
I'm
Thanks.
sorry, but yeah, no problem.
Okay.
So let's continue. So we can see that this H2O flow is very like a Jupyter Notebook or MATLAB. So a few things I want to show you first is that first the admin page. This one will give you a job list. Right now there's a new session. I haven't submitted any job yet, so there's no jobs. And each job you will be assigned with a virtual kind of a cluster. So you will see this is all the resources we have. For each user, you will have a 16 CPU cores. So considered as a cluster. It's not much, but the example we're gonna run is relatively easy today. So it's more than enough. And then there's a water meter. The water meter shows the current activity of CPUs. So give you a visualization of your current resources usage. Following it, there is a few drop-down menus, give you how to find out list the data, list the model, see the list all the prediction results, and yeah, that's pretty much. It's very easy to use, and we're gonna jump back to my slide, and we start today. Continue our today's presentation. So machine learning has 3 main functions. 1, classification, 2, prediction, and 3, clustering. So for each basic main function, there is a very simple and basic algorithm. For classification, the simplest algorithm is the k nearest neighbor. For the prediction, the most iconic one is linear regression. And that's for clustering. the most popular is the K-mean clustering. Besides that, other common algorithms also including naive Bayes, decision tree, random forest, support vector machine, and the PCA, and so on. Today we're not gonna cover all of them, but only those that supported by the H2O law. First is the K nearest neighbors. For K nearest neighbor, an object is classified by a majority vote of its neighbors. This is one of the most simplest classification algorithms. It's often used in classification. It computes from a simple majority vote of the nearest neighbor for each point. The K is a constant specified by the user. So M, the KNN, is computationally expensive. As we can see, choosing the factor K could be a challenge. As we can see from the right-hand side plot, with a different number of K, the boundary becomes smoother with getting smoother and smoother along with the increasing number of K. But again, with this, the computation amount will also increase too. The pros and cons. The pros for KNN is that it is beautifully simple and logical. The drawback is it may be driven by the choice of K. Sometimes you have a bad choice, then you will get a bad result. Second one is linear regression. Linear regression is a very simple and elegant method to predict values. So let's take an example. How to predict the house price. Okay, we all know there's many factors can affect the price of house. But for this case, we simplify this model, which means that the price of house only related to the living area. So basically, the bigger the house is, the more expensive the house will be. So how to, just as shown as the right-hand side plot, based on the size of living area, the linear regression will find a best fitted regression line to represent all those data. So for the prediction, if we had a new house with a certain living area, we can using this regression line to find this find the house price accordingly. How to find this best fitting line? One option is to minimize the sum of square differences between the data point and the regression line. As we can see, if there is a line pass through all the data points, we're gonna calculate the distance between the data point to the regression line, and sum them together. So just like we can see in the middle column, to minimize, if we assume this line hx equals to theta 0 plus theta 1 plus, multiply with that, then the theta 0 and theta 1 will be the parameter, and then the cost function j theta 0 theta 1 could be represented with this formula. And then the whole problem is to how to minimize this cost function. There's two methods to solve this problem. One called the normal equation, which is a closed form. Basically, this is just to solve theta 0 and theta 1 analytically. This direct closed form equation can calculate the theta 0 and theta 0 and theta 1 without iteratively optimization. So it will be very concise and elegant, but due to the computational amount limitation, it is only suitable for a small feature set, let's say less than 1,000 features. If the model is really big and the data feature is larger than 1,000, using this normal equation method is not worth it. The second method called gradient descendant, which is the most popular and optimization method for not only linear regression, for quite a lot of machine learning and deep learning algorithms. So this is using an iterative optimization approach to gradually tweak the model parameter to minimize the cost function over the training set. So eventually, it will converging to the same set of parameters as the first method. Gradient is a better choice than the normal equation when there's a large number of features or too many training instances to fit in the memory. A gradient is a slope of a function at a specific point. The gradient loss function is equal to the derivative, which is the slope of the cost function curve. As we can see, basically the parameter will be iteratively updated in the follow equation. The new theta, the parameter will be equal to the old parameter that parameter point that minus the learning rate, which is a hyperparameter, multiplied with the gradient of a cost function at the point theta. So which means is that when we have a set of a parameter, we're gonna calculate the gradient of the cost function, and then move the next data point to the opposite direction, so that by doing that, one small type by small type will decide by the learning rate. Iteratively, this result will the data will meet at the global minimum point and stay there stable. So we know that we have find our solution. This is an example that how to iteratively find the best fit line through gradient descendant algorithm. So we have a set of data points, and we want to find a linear line which show in the right line, and to feed those data sets. And as we can see, our cost function was being plotted on top, that we have a parameter M, we have a parameter B, which represent the theta and theta 1 parameter for our previous previous example. And the z-axis represents the sum of errors. So at first, we have started at a random point and with a very relatively high error. And then we calculate the slope of this cost function curve. It's actually it's a hypersurface. And then we're gonna using iteratively find the data point closer to the global minimum of this cost function. And for many iterations, we eventually will find out the closest point, which is shown on the right-hand side. We can see the progress of for each iteration. So unfortunately, these two methods are too easy, so that it's now very hard to implement. So H2O AI Flow doesn't support them directly. But this third one, the K-mean clustering, is the first method we're gonna show you within the H2O AI Flow. The K-mean clustering is discovers the structure within the unlabeled data. So clustering is a technique to find a similarity group in the data called clusters. It attempts to group individuals in a population together by similarity, but now driven by a specific purpose. So clustering is often called a unsupervised learning, as you don't have to pre-describe label in the data, and no class value denoting the a priori grouping of the data instance are given. This is the workflow of the Taming clustering algorithm. So from the subplot number 1, we have a set of data shown in gray squares. Let's say we want to classify this data into three groups. So the first step is we will choose 3 initial centroids, which show in the red, green, and blue red round dots. The second step is we will calculate, we will group each data point to the initial centroid by purely based on the distance the data point to the centroid. So as we can see, the second subplot, we see all the data points, which is previously gray, has been colored with its different its closest the centroid point. And then at step 3, we're gonna move the new centroid point from the old centroid point to the mean of the data set. So which means we move the centroid point since the group in red has only 1 data point, so the new centroid point move to that data location. And we can see the green group have a lot of data points. Then we're gonna calculate the mean, the value, and move the new centroid point to there. The same happened to the blue group. And then we have a new centroid point. And we're gonna repeat the step 2 and 3. So calculate the grouping the data point to the closest centroid, and then move the centroid to a new point that is the average center of the group from the previous iteration. So Step 2 and 3 are repeated until the convergence has been reached. Eventually, we're gonna see the centroid point is moved to this location, and all the data point has been clustered into 3 different groups. The weakness of k-means is that first is, of course, the number of k must be specified in advance. The k-meaning clustering is very sensitive to initial centroid point selection. A bad choice of initial centroid point can lead to unwanted solution. And k-means can only handle the numerical data. And sometimes algorithms may get stuck in the local minimum rather than the global one. And the k-mean, since every iteration, they will take all the data points into consideration with the same weight. So it's very sensitive to the outliner and noise, which will result in inaccurate partition. So k-means also cannot handle different like a globular cluster or cluster with different size and density. As we can see from the bottom of this slide, we have 3 examples showing that k-means one handling the different type of data that may not have a very good solution. First is that one dealing with different size, and then is that clustering the data sets with different density, and then is non-globular clusters. We can see the two different group of data point is swirling together. For that, is the k-means clustering is very hard to handle the situation like that. Okay, so now is the hands-on time. So as you may already know, I have already pasted it's actually one line import file in our chat. You can copy this immediately, copy and paste. I will do the same thing. We're gonna use this very small data set throughout the presentation. So you only need to import them once. And basically, this is a variety of weak data sets. Basically, it's just measurements of geometrical properties of the kernel belongs to 3 different types of weak. We can see there are 3 features: the area, the perimeter, the compactness, the length of kernel, width of kernel, and so on. So it's a very small data set, and so it's very fast to just show the functionality. So let me get started. Let's see, do I have this one? Okay. So basically, we want to start a new flow, create a new notebook. And the first is to import. This is very, this H2O flow is very easy to use. So you only have a few steps. Import the data, parse the data, split the data if necessary, and then you can build a model and see the result, and make a prediction if you inference if you have data to try, and then also you can save the data for further use. Let's get started. Okay, very easy. Import file. I already imported data set. And the next step is I will parse this file. As we can see, those data is this parse. The divider is a horizontal tab. We can leave it as default. The system will automatically try to find the divider for us. So most of the time you just leave it there. But the separator, you can see there's a lot of different space, right, or comma, or the different symbols. But basically, it will auto detect. And then we can see all the data has been shown here. There's a 7/8 column. So the first 7 column is the first 7 features I show you in the previous slide. And the column 8, you can see it's actually integer number 1, 2, and 3. It's the variety index of to represent different type of week. And then simply parse, press parse. You can see right now the HAL H2O flow already reading this data, and we can see the data is showing here. This is minimum, maximum, mean. So we can see the data type. And since we do not have a label listed header files within the data, so it will just throw for column 1, 2, 3 to 8. So now what should we do? For machine learning, we want to have a training data set and also the validation data set. But for the unsupervised training, it seems we do not necessarily do that right now. But we can still do split the data here for the following test. Click split. So I'm gonna split this whole data set into a 2 parts. One called I will call the train. One called valid, which the ratio is 75% and 25%. You can split into more the data subframe. Like you also want to test the frame, you can do that. We just save some time here. And also you don't forget to give a random seed to make sure the randomness to select to random select the data from the data set. Click. We have the split the frame ready. And then next step is to build a model. Build a model here in the H2O flow. H2O do have a R and the Python API. So which means if you want to program that, you can do that without any problem. And but if you want to use H2O flow, you need to only you can either have your program the model get import here, or you just using the built-in model. Let's just choose the k-mean. By using k-means, we can have the training data set and the validation data set over here. And also, if we want to use k-fold cross-validation, here is the field to input. Normally, I think the go-to value is 5. So then, which means 80% of data will go to the training set, and 20% will go to the validation. So if you want, you can try that. Actually, considering we are having a very small data set, using the k-fold cross-validation seems like a good idea. But I just saved some time. We got to now using this. If you want, you can try that with your own H2O flow instance. So here is the thing. So here is the ignored column. So as we may know, the first 7 column is the feature, and the 8th column is actually the label. But we do not want to use that. This is the unsupervised training. We do not want to give them the label. So we ignore the column A. So this one will be used within within the training. And here is some different. Here is some following parameter we need to decide before the training. First is the K number. We already know that we have 3 different variety of weeks. So the K is 3 in this case. Also, if you really do not know the K, you can estimate K, whether to estimate number of the cluster iteratively, which gonna cost more time, right? For max iteration, I think 10 may be a little bit too short. Maybe we want to do, let's say 30. And always we want to standardize the data, which is always a go-to option for machine learning and deep learning. And then the initialization mode is how to choose the initial centroid. As I mentioned, this is a quite the important choice. So here has 3 different ways. The random, which just like it means, it's a random select the 3 centroids and start the computation. And the plus is random selecting the first centroid and using their algorithm to find a relatively far away point as their second centroid. And the furthest, this is also very straightforward, is a random select 1 centroid, and the rest 2 will by default using the furthest point as the initial centroid. I will prefer the furthest, but you can try different ways. You can play with these different initial points to see the initialization mode have a very huge impact for the final result. And then for the advanced and the expert, the parameters, we do not cover in this presentation. You can try yourself if you have time, but let's start build the model. As we can see, it's very fast. And then this is done. We can view the result from here. As we can see, for each iteration, for the Taming clustering method, how do we measure if the K clustering is doing a good job? The measurement we use is called within cluster sum of squares, which is which means that after each iteration, we're gonna calculate the distance, the squares of distance between the central point to each data point and sum them together. The smaller this value is, the better the training job is done. So as we can see, we have a pretty good curve iteratively. Every time this is, we can see the number of within cluster sum of squares are reduced, and we can see the model summary, history of scoring. We can see only 5. We only need a 5 iterations. We already reached this minimum result, get stable. So this is all the training. Okay, so let's see this. So the Centroid static. So this is the training set. After with the clustering, the 3 data points, each will have this many of data, right? And the sum of squares is like this big, and then we go to the validation set. We can see the data set is getting smaller, so that of course the sum of the squares value is getting smaller. But we can see that it's pretty much the data set is 1 to 3, right? Basically, so if we multiply this with 3, we can see this is a relatively comparable result, which means this is, I will say maybe a little bit overfitting, but overall it is considerably good. Right, this is standardized cluster means for each century point. So because we have 7 features, so we can see we ignore the 8th century. Otherwise, that one will be the dominant factor that will influence the final result. All right, this is for the k-mean. Let's jump back. So is everybody following this? Is the H2O flow working? Please let me know. Oh, there's slide 11. Please, can you please paste the link again? Okay. It's on the top of our presentation. I will paste it again, and then share data. Can you please? Okay, yeah. Oh, thank you. Yeah. Okay, I saw C8. Probably something was there. Was put in the input. Yeah, all I saw was CA2. Oh, yeah, it's yes. So as I mentioned, it's when you build this model, you have to ignore column. You need to like click this one to ignore that. It's you need click this to ignore. Yeah. So yeah, it's okay. But you can see, we already did a K-clustering machine learning task with 0 amount of programming, even that 3, right? This is the reason we introduced the H2O AI into our cluster. If our users have some data sets, they want to have a quick baseline result, they can always use this one to give you some preliminary results. And let's continue. Naive Bayes. How was the data split? Okay, so data split is when you parse the data being read in from whatever the data was, CSV format, into this HEX. Here has a split button. You can split here. Okay. All right, so let's go to naive Bayes. Naive Bayes is a simple but important problematic model. It's based on applying Bayes' theorem with naive assumption of independence between all the features. We compute the conditional probability distribution for each feature given label. And then it applies Bayes' theorem to compute the conditional probability distribution of label given an observation and use it for prediction. It classifies the new data based on the highest possibility of its belong to a particular class. Naive Bayes learner and classifier can be extremely fast compared to more sophisticated methods. Let's get to some details. First, this is the very simple and elegant formula for naive Bayes. So the P means the probability. So this formula means the probability that A upon B equals to the possibility B, condition B, A upon condition B is equals to the probability B upon condition A multiplied with the possibility of A divided by the possibility of B. So, example, should I play tennis or not? Here, I have a data set. Basically have 4 features and 1 label. 4 features is outlook of the sky, the temperature, the humidity, and the strength of the wind. The label is if I play tennis or not. So from this table, we can collecting those possibility information, like if the outlook of the sky is sunny, the possibility I play tennis is 2 in 9, and I didn't play tennis is 3 out of 5. And if the outlook is overcast, the possibility I play tennis is 4 in 9, and I don't play tennis is 0 out of 5. So just like such, we have created this possibility table, and then it's time to how to implement this possibility to calculate, to make prediction of my behavior. All right, so let's say if the outlook is sunny and the temperature is cool and the humidity is high and the wind is strong, then should I play tennis or not? So if we just implement the formula, the possibility I play tennis upon the condition X equals to the possibility is equals to the possibility I play tennis under the outlook sunny, temperature cool, humidity high, and the wind strong equals to given the condition I play tennis, the possibility of sunshine, of outlook, of temperature cool, humidity high, and wind strong, multiply with the possibility I play tennis, and divide by the possibility of such condition happens together. So just following all this formula, and we can calculate the day I play tennis, the possibility is 0.2424, which is like 24% of chance. And then similarly, we just calculate under the same condition, the possibility I don't play tennis. So after a series of calculations, of course, we can see the possibility is 0.421. So which means there's 94% of chance that I won't play tennis. So also we can see the wind strong or not is a really important variable. Some people will argue, okay, the temperature cool could also contribute to that. But as a student been living in Wyoming for 5 years, I tell you, temperature is never the case that stopping us to play tennis. Okay, now let's implement the exact same data set with the naive Bayes method. Okay, so now let's see something. First, if you click the data drop-down menu, you just list all the data frames. You can see I have the whole data set over here, the train data set here, and the validation data over here. I also already have a model that is called K-mean. And now what I want is to start a new notebook for our naive Bayes task. So, but remember that the cluster of H2O flow is not closed. So I do not need to import the data again. I can just directly build a model, naive Bayes, and fill unfold. Do I want to do folding? I do not want to do that. So click the training data set, 75%, and the validation data set, 25%. This time, we have a response column. The response column is actually another name for label. So in our case, it's CA. Yeah, so because H2O is an English-British company, so they call everything differently, I guess. So we already clicked the response column at CA, so we do not need to ignore the column CA again here. Also, you can click it. It doesn't matter basically. And there's a few parameters that you can tweak yourself later. And we just directly go through, okay. Oh, okay, yeah, I forgot. It's actually in my slide. First is, people gonna ask, so the example I given, all the data is either wind or no wind. It's a sunshine or cold, or it's a category data. How do the naive Bayes dealing with numerical data? So I've been checked very carefully, but I didn't see how H2O flow solve this problem. But in general, when dealing with numerical data, we basically will calculate the mean of, like there's a numerical feature, we're gonna calculate the mean and use the mean to calculate the standard deviation, and use the standard deviation and mean to calculate the normal distribution. And the ratio of distribution will be used as the probability of a certain feature giving certain the as the possibility. And then also, the naive Bayes only accept the catalog data of label. So the current data set we have is actually a integer. It's an integer type. So we want to convert them into new type. Let's do that right now. All right. So let's start. Let's go to the data. I will list all the frames. So let's first go in here, click the train data 0.5. We want to convert this C8 to enum. Done. Similarly, we want to click the validation data set also to enum. Done. And then we can go back to, I don't know if we want to reselect it again, and basically the same. And let's build the model. Now it's accepting it. Let's view the result. So since it's a possibility tree, you can see, compare with the K-clustering, I mean the computation is very fast because this one do not need iteratively calculation. All they do is just calculate the possibility and based on the based on the formula of the naive Bayes. So we can see for the catalog 2 and 3, the training data sets and validation data sets are all doing a good job, but the hit ratio of catalog 1 in valid training data set is 93%, and for validation data set is 88%. I mean, it's a little bit, let's say, overfitting, but I mean, we can always optimize the parameter to see we can have a better result, but that is not our not today's job. We're gonna continue. This is only show how to show you what the result looks like, and we're gonna jump to our next machine learning algorithm, decision tree. The decision tree builds classification or regression model in the form of a tree structure. It predicts the value of target variable by following the decision in the tree from root, which is the beginning, down to a leaf node. A tree consists in branching condition where the value of a predictor is compared to a trained weight. Decision trees are prone to be overfitting, so additional modification or pruning may be used to simplify the model. A very straightforward example. How to growing a tree to involve deciding on which feature to choose and what condition to use for splitting along knowing one to solve. Okay, we have a data set on the right-hand side. Those blue triangles indicate the people do not attend the Burning Man event. And the yellow round dots is the people that attended Burning Man. So how do we build a tree to classify those people? First is we set up is the per people income less than 71K. If yes, yeah, majority of those people with income less than that won't join the Burning Man event. And if not, if the age is less than 27, if yes, then this part of data people don't join the Burning Man event. And then if no, which is this portion, is the age less than 38? If yes, the majority of data inside this region attend the Burning Man event. The one larger, older than 38 years old, is not attended the event. That's how it works. But how do we build a tree? So to measure how well we build a tree, we need to introduce a term called entropy. The entropy is a measure of the disorder and uncertainty. The entropy is a concept used in physics, mathematics, computer science, and other fields of science. The concept of entropy originated in the thermodynamics as a measure of a molecular disorder. Entropy approaches zero when the molecules are still and well ordered. So the higher entropy, the particles are high disordered, messy, and random and uncertainty. So building a tree, so mathematical, how do we define entropy? Let's say here is the formula. The PI is the possibility giving the ith value when randomly select one from the set. So here's an example. Inside this circle, we have exactly 30 data points. And 16 of them are blue circles, and 14 of them are orange cores. So if I pick, let's say there is one circumstances, if all 30 of the data points are blue dots, are blue circles, then each time I pick one data will be blue circles, which means this is very stable, very ordered. So if we, the possibility is like 100%. So if we follow this, and then also we follow this entropy, which means the entropy will be after calculation will be zero, which means this data set is completely stable and certain. So what about this one? We have 16 out of 30 blue circles, and also 14 out of 30 orange cross. So which means the chance is of me picking a blue dot or orange cross is roughly 50-50. So by putting those numbers into this formula, we can calculate the entropy is 0.99, which is a very high entropy, which means this data is very high, it's highly disordered. And for building a descendant tree, we need to, the key is just to reduce the uncertainty into certainty. So let's see, still use the play tennis example. So when the weather outlook is sunny, we have 3 days, 2 days play tennis, 3 day no. When it's overcast, 4 day play tennis, 0 day no. Raining day, 3 day play tennis, 2 day no. So what we want to use to divide the next tree branch is we calculate the purity of the split. So this one is called a pure site. So it's completely 100% certain. So this is a very good fit. And this one, so when it's strong, there's a 3-day isolateness and 3-day no. This is an impure site, which means completely uncertain. It's a 50-50 chance. So we calculate the entropy is exactly 1. And building decision tree have a lot of algorithms. We only gonna introduce 2 very popular, well-known ones. First is called ID3. The ID3 is use the information gain to decide if the purity of measure the purity of the split. So the information gain is equal to the entropy before the branching and minus the entropy after the branching. So let's see the example on the right-hand side. The entire population is a 30 instance, and the parent, which means the entropy before, has a entropy of 0.996 as we calculated before, and then based on certain rules, we branch them into 2 subsets. So the first subset have a 17 instance, which have 4 blue circles and 13 orange crosses. And then the other one, we have 12 blue circles and 1 orange cross. So we can just put those numbers to calculate the entropy, and then we can see the entropy child number 1 has a entropy of 0.787, and the entropy that child 2 have an entropy of 0.391. And if we multiply by the population portion, we can calculate the overall new entropy, and by multiply the parent and minus the children entropy, we can see that the information gain is 0.38, which means we cannot say it's a good or not good, but at least this split did help classification of this classify this data set. And another decision tree, the building algorithm is called CART. The CART is using the Gini impurity index to decide if we want to split the branch or not. So the Gini impurity formula is shown here. Is basically 1 minus all the probability square. So for this instance, the Gini impurity, then if the chest pain, we based on the chest pain, we gonna say the user has heart disease. It's 105 people, and do not have heart disease is 39 people. So the Gini impurity is 1 minus the probability of yes heart disease and the probability of have no heart disease. So based on that, this is the formula. We calculate the impurity of this for this split. So how do we build a tree using this CART algorithm? First, let's say we have 3 features to choose to split the tree. So the first is the chest pain. Second is good blood circulation. Third is blocked arteries. So for all these three different different features, we're gonna calculate the gene impurity. So gene impurity for chest pain is 0.364, and for good blood circulation is 0.36, and for blocked artery is 0.38. So which means the good blood circulation is actually has the least gene impurity, which is the best choice we choose to build this tree. So after that, we still have two features to choose. So we're going to calculate the gene impurity index again, and use the block artery have like a smaller gene impurity index. So we're going to use that for the second branch, just as shown in this one, in here. Also, if like we also know the impurity of each branch, we can also measure the gene impurity before and after the split. So if the gene impurity is actually increased, like from here, so for the blocked arteries, if for this branch, it's no the blocked artery, we already have a very little impurity of this data set. So if we want to split further, we might actually increase the gene impurity. So if that's the case, we just do not further split this leaf. So by this one leaf after another, we can finally build a tree just like this, which we can see the final result. But the data has been very neatly classified. And then another question is, those are also yes or no kind of a binary data. And what about the numerical data? So for the numerical data, we will basically calculate the means between the two features, so that based on this mean, we can also calculate the impurity the index, and use the smallest gene impurity index for the branch split. All right. I think there's a lot of merits of a decision tree. First is it's very simple to understand and to interpret. And to build decision tree require very little data preparation. It can handle both continuous and categorical variables. It implicitly performs feature selection. The drawback for the decision tree is they are very easy to overfitting. You can create biased trees in case of unbalanced data. Sometimes it could be unstable. And the greedy approach used by decision tree doesn't guarantee the best solution. And standard decision trees are restricted by hard access aligned split of the input space. Talking about decision tree, but another term is more popular, is called random forest. The random forest is actually one of the most used algorithms, which is based on decision tree. So just like just like the forest means a forest is a lot of trees. So the random forest is basically the bagging algorithm plus the full-grown card decision tree. So as we can see from the figure down below, random forest is randomly selecting a subset of features from all the data and using this subset to build a decision tree. And each decision tree will predict a result. Using this result, we can to use for our final prediction. We can use majority vote, or we can use average methods to decide which class this data should go. So just like this chart said, there's 3 different trees. Each tree will make a which will have a possibility result over here. And then for this, we're gonna make a summation of all these 3 results. And using all the considering all the results, we can this is the final result is obtained by averaging all 3 probability distribution, which will give us a more stable result compared with the single decision tree. So the merit of random forest is that the random forest algorithm can be grown in parallel, which is very good for our highly capable for computing system, especially with the GPU. The random forest has higher classification accuracy. That is because we can do some feature selection, and the random select subset we will avoid avoid overfitting. So it's able to deal with missing values and maintain accuracy in case of missing data. It can also help data scientists to save data preparation time. This is a very big feature. The drawback of random forest is that large number of decision trees in random forest can slow down the algorithm. And good job at classification, but it's not as good as for regression. And random forest, like a black box approach, random forest is not easy to interpret. And again, let's start our same data again. So, all right, we have our K-mean, naive Bayes. Now is to create a new new notebook, and we're gonna create a distributed random forest. And then the training frame, 75%, validation, 25%, response, column C. And here, how many trees do we want to build? 50 may be a little bit too much. I will do 20. And max of that, because we only have 7 features, 20 is obviously overkill, but this one is just a maximum tree depth. So because we only have 7 features, I don't think anyone can hit this far, right? So also there's other parameters. We just leave it leave it as default, and then we can build the data very fast. We can see the result. Here is the result. The blue line represents the training data set. The orange line represents the validation data set. As we can see, here, actually the random forest did a pretty good job. I mean, it's not only the very good for the training data set, the validation is doing a good job too, which means we do not have any overfitting situation here. All right, so here is the result. I mean, look at that. I mean, the last figure already plot for you. So you can just copy and paste into your slides and or your paper. Because I think it's a very unique, not very unique, it's a very convenient feature for our users. And another thing is that the variable importance, this chart, this is basically shows a contribution for each feature. As we can see, each feature represents one a different feature of the kernel of the wheat. So we can see the C1 obviously contributes a lot, which is the area of A. So basically, these three different types of wheat are mostly distinguishable by the area of the kernel, right? So this is important because with this variable importance table, think about that. We only have 7 features, but I know some of our users have data sets have dozens or the hundreds, even thousands of different features. I mean, are those features are all important to the algorithm to achieve the solution? Maybe all of them. So maybe we can feature select the most important ones so that we can not only save a lot of time, but save a lot of time and the computational resources. We can also get rid of the noise and the bias, the data point. Another thing I want to show you is there's a training and validation confusion matrix. So we can see here that here is the training data set. Here is the precision. Here is the recall. Here is the first kind of wheat that being misclassified to the second category and the third category. So based on that, we also even the confusion matrices is prepared for you. Copy and paste to your paper, very easy. And also based on that, you can further calculate. I think you can easily port these into your Excel. So if you want to calculate the F1 score, and it's just a very simple formula input. So as we can see, this is a very convenient tools for our users to have a very fast preliminary result if you have a new data set and do not know what to do with it. And then people are going to ask, if we compare the random forest, this one seems not have a better result compared to the naive Bayes, right? Then what should I use? I have a data set. It's a brand new data set. I do not fully understand the data set yet, but I cannot decide which method is best for me. What should I do? Then following is a very important feature which I enjoy this H2O AI flow the most, called auto machine learning. Auto machine learning right now, I think it's getting hotter and hotter. There's other, I know sklearn already have auto ML already. And I think there's more and more machine learning framework supporting that. This AutoML will enable the non-expert to train high-quality data learning machine learning models. It can improve the efficiency to find the optimal solution to machine learning problems. The H2O law, you can utilize the gradient boost machine, the random forest, the generalized linear model, and the deep neural network. Again, there is no free lunch, so AutoML is very slow due to a very heavy workload. Let's get started. So here at the very in the very first choice is run AutoML. So let's say I have this data. I do not know what to do with it. Which method is best for me? So I'm gonna choose first the training data set, response data set, the response column, CA, validation data set, the 25%, and then give them the name. I will say wheat 3, and then also weight column and ignore column. We do not need to do that anymore because we already have the response column. And then one more thing is this is important, is exclude algorithm. Is that by default you will use all these 6: the generalized linear model, distributed random forest, the gradient boost machine, deep learning, stacked ensemble, XGBoost. All these 6 models will be used. But in some cases, a certain method won't be good for your training. You can just exclude them out. For today, I will exclude the deep learning. It's not. I need to be clear. It is not the deep learning is not good for this data. It just deep learning is relatively computational intensive, expensive compared with other methods, which will slow the whole progress down. If you want to try out yourself, you are more than welcome to use all those algorithms to find the best one. And then there's a max model and the max runtime seconds. Let's say I only have 5 minutes. In the 5 minutes, I need to find out which model is the best. I will just input the 300 seconds, and then the whole thing will run for 300 seconds. It will randomly select different methods with different hyperparameter, and then we can see what's going to happen. So build model, it is building. Now, I mean, it's halfway there. We can see, monitor them alive. We can see, okay, the 4th one is here. 5th one, right? So each represents a model. This one is used, for now, the best one we have is gradient boost machine. Okay, now this is a stacked ensemble. That's of the family coming second. So this is based on we can see based on the value of the mean per class error, we can see which method is doing a good job, and there's already more than, I think it's more than 50 already models there. So let's say, okay, they're still going, but I want to see this one have the best result. I want to see this one. So I'm gonna click click this model, and I can see this one is the gradient boost machine. As we can see, okay, this one is obviously overfitting, but we can see all the results over here. Is this a good model, good choice? And or can we just, this one, since this one is overfitting, can we do something about it? Maybe further tuning the parameters and always adding more data to train or to train. I mean, think about that. The whole data set only have 210 data points. It's a very small data set. So if it's overfitting, I don't blame the algorithm. I will mostly blame about the data set. So as we can see, this is the result. We can see the lost figure. We can see the variable importance, the confusion matrices. So this is pretty good. And if we want to see, okay, this is a gradient boost machine. It's kind of the best, probably the best model we can find for this this chart leaderboard. Let's see if I can find something else. Wow. Like, no. I mean, look at that. I mean, it seems that the gradient boost machine is the best model for this problem. So that gives us an idea and point out the way where to continue the tuning of the model, right? So yeah, I think I have show you all the material I want to show you. So so basically, thank you again for joining us today, and thank you for your time. We still have 20 minutes left, so I will be here waiting online. If you have any questions, please just write in the chat, and I will answer them as I can.
Hi, David, do you have email address? So if in the future, if we have questions, we can email you.
Yes, I will put them in the Slack chat. And also, if you log into our HAL on-demand portal, there's ways to contact us. There's a ticket system. There you can join our Slack channel, which is the most convenient way to contact me directly. And yeah, and also join our Slack channel. And our user group is very friendly. I mean, even while I'm not around, I saw many users helping each other in the Slack channel. Yeah, it's very helpful.
I have a question, David. This is Sandeep from NCSA. So in the previous like auto ML example, that you know, you basically like showed the best model and then suggested that it is kind of like overfitting, right?
Yes,
so,
yes.
So does that mean that it is using like training loss to select the best model, or is it still using the validation loss, just that, you know, this is still the best all the models, you know, could do?
I will say probably if we can check that this is the best one, right? We can also select I think it's just average or some measurement, because we can see, we can find the 13 one, they're pretty much the same. I will say if we check closely to the leaderboard, it's actually they are not that different.
Right, but is this the validation error or in the training set? This would be the validation in the validation data set, right?
We can see. Let's see.
Okay.
I mean, for that, I don't know if I can answer now, but I need to check the website to give you the answer. So
okay.
Let's say the data point. I think you know I mean, I think it's
Yeah,
a
0.02.
detail.
Yeah, right.
Yeah, it's zero. This is 0.4. This is 0.1, and I think it's somehow. I think it have its own measurement, but basically, relatively, this still represent this one is better than that one. Doesn't mean the best model is guaranteed to be not under or overfitting, right?
Yeah.
It's just error measurement.
Okay. Yeah. Thank you. Thanks.
Okay, if there are no more questions, Davai, thank you very much for this very informative presentation and the demonstration of the tools. So with that, we will conclude today's tutorial, and we will continue next week. Yeah, so Davai, thank you very much.